Okay, the mineral science, right? The mineralogy and mineral science, the study of chemistry and atomic structure, and also the properties, right? Regarding their genesis. What is genesis? Genesis means the formation of the minerals. Okay. Right. So you have already learned about this definition, I think, about the mineral definition. This is not the definition, but just an introduction about the mineral science or the mineralogy, right? When it comes to the optical properties, that means the properties that we learn under optical microscope or the petrological microscope or otherwise polarizing microscope, right? Then we call such properties as optical mineralogical properties. Okay. So the scientific aspects that we learn under that related with the microscope is called optical mineralogy. But generally, mineralogy is a broad science which covers many aspects, including some mainly the chemistry part. Right. So subfields of mineralogy, you may have learned that we have broadly two subfields, that is descriptive mineralogy and optical mineralogy, right? So the descriptive mineralogy, the one that we are now learning about, and there we consider mainly physical properties, right? Under optical mineralogy, we mainly consider optical properties. Optical properties means what we can see about minerals under transmitted or reflected light, right? With the aid of light. So the another branch, a main branch, is crystal chemistry, right? So the crystal chemistry is the relationship of chemical composition to atomic structure, because you know the minerals are crystallized in different crystallographic systems. So their composition has a different specific arrangement, and due to that we can identify some crystal structures or atomic structures in minerals also. So it's not just a compound, it is a compound with a specific shape, structural arrangement. So therefore each and every mineral has a specific structure, a shape of the crystal. So because of that, we can identify different minerals. And there are some other materials, chemical substances, they look like minerals, apparently or physically, but actually they are not minerals, because we do not take them into the mineral group since they are lacking a specific crystal structure. Can anyone tell me or guess such a material, such a substance which looks like a mineral, but we don't consider them as minerals? We have a specific term for that group also, because these are called crystalline materials, right? Because they have a crystal structure. What are the other types? One group is there, which is non-crystalline materials, which are called? Anyone? Guess? The materials which do not have a specific crystal structure, but they have other properties. They have a chemical compositions, definite chemical composition, naturally occurring, all the other features are there, because for a mineral, we need some specific criteria, right? They satisfy, but except the structure. How do you term them?
Amorphous.
Sorry?
Amorphous.
Very good. Yes, amorphous materials. Okay. Yeah, I can see in the chat line also some materials are put there. But water is a liquid phase, which we do not consider as an amorphous material. Okay. Amorphous material are those. For example, chert. Right. Chert, it's a silica, SiO2, silicon dioxide, right? Like quartz, chemically. but they do not belong to mineral group because they don't have a specific structure, right? So amber, it's a organic type of mineral, right? Amber, pearl, like those things, right? They are amorphous. They don't have a specific crystal structure. Right. So such materials are there. So anyway, for genesis of minerals, we have to consider geologic setting, right? That means physical conditions, chemical conditions, and structural criteria or attributes to their generation or their production is different from each other. For example, you can understand Sri Lanka is famous for gemstones, right? Although we call it gemstones, they are not stones actually, right? They are also minerals. They belong to mineral family, but specific group of minerals, gems. Do you know why we say categorize gems as a separate group? Yes. Anybody? Why do we call minerals, some one group of minerals as gems? Although commercially people used to call them gemstones, like stones. Actually, we find them like stones, like beautiful stones uh, from the soil. Therefore, people commercially or average people term them as stones. Actually, they are not stones. They are also minerals, right? But these specific minerals, yes, yeah, very good. Somebody says it's due to hardness and luster, right? Yeah, those are some properties. So generally, we term these gems as having durable some specific qualities, right? They should be beautiful, right? Beauty is one quality, and they should be rare. Rarity is another quality, right? And the other one is durability, hardness, and everything, right? It comes under that durability and luster and various shapes and various shades of colors, they comes under beauty, right? So beauty, rarity, and durability, those are the three basic aspects for a mineral to be categorized as a gemstone, as a gem variety, gem mineral, right? It's better to say gem minerals, right? So these three categories are, I mean, at least one of those features are lacking in many minerals. Therefore, we don't categorize them as gems. And you know, because of these three feature, for example, rarity, if it is very rare, and also if it is very beautiful and also durable, then it adds more and more value to that particular mineral. So therefore, gem varieties are expensive compared to other normal minerals, and also they are durable, so you can use it for many purposes because of the durability. For example, if you have a feldspar, right, beautifully cut feldspar into a shape of a gem, right? But with time, it decays and it weathers out, right? It's not durable, right? It makes into soil, right? Or clay minerals, right? It converts into clay minerals. You can see in rocks when you go outside. These feldspars are easily get weathered. You know, weathering. Weathering is a decaying due to physical and chemical agents, right? But if you go to the field and discover a gem like ruby, sapphire, or zircon, or monazite, or something like that, you can still see they are very well preserved as it's a beautiful stone, right? It's a durable stone. So therefore, it adds an extra value for the gem varieties, for the mineral quality. So therefore, we consider them as gem varieties because of those specific properties. So as you know, how many, in average, how many minerals are there discovered in the planet Earth? How many of minerals are discovered in the planet, and how many are considered as uh, gems, roughly? How many known minerals? Approximately. Okay, someone says 4,000 species, like, yeah. Another one says 3,000. Yeah, actually around 3,000 minerals are discovered, and if you take species wise, it might come up to 4,000. That may be correct, right? Around 3,000 minerals are discovered, and how much will be like how many will be like gems on the gem category approximately? Gems are also categorized: very precious stones, semi-precious stones, like that. There are about 150 gem varieties, maybe, gem minerals. Maybe with varieties, it comes up 200 or so. Okay, so you can understand how rare they are, right? So out of 3,000, you will have about 200 minerals, right? So that means 200 gems, right? So that means it's like a very little amount, right? And also, if you see their distribution, right, globally, you will see very difficult to find them. Those 200 minerals or 200 gem varieties, it's very difficult to find everywhere, right? They are restricted to some regions only. So why is that? And also that adds another extra value for that because of the rarity. That is the rarity. So why they are not found everywhere? But you can see quartz, feldspar, everywhere you can find them. So they are not rare, right? In every country you have quartz, feldspar, biotite, like minerals. Okay, so they are not rare, and also they are not durable. So therefore, we don't bother much about those for counting as gems. But gems are distributed in very restricted areas. For example, Sri Lanka is famous for gems. And what else? What are the other countries famous for gems? Brazil, right? Brazil also has very similar gem varieties to ours. Okay, you will learn why that is later on in a different course unit. Okay, and at the time being, for the time being, you can start learning by yourself why we have. I mean, Brazil has, or South America has similar gem varieties as ours. What are the other countries that have similar gem varieties to ours? Anybody knows? Just name one country, another country. Very good. Madagascar. Yes, Madagascar. And East Africa. Okay, Eastern Africa. You have such similar gem varieties, and also India, southern India. We have not northern India, but southern India. You have similar gems to ours. That has a reason. So you can find the reason here even if you think a little bit deeper regarding the mineral genesis. So I have here mentioned about geological setting for mineral genesis. So that is very important. So pressure and temperature conditions are very important for formation of these specific group of minerals. Of course, PNT, or pressure and temperature, is important for all the minerals to determine their formation. But for the specific minerals, that means gem varieties, to be formed, they need specific geological conditions. Specific geological conditions means some prefer very high temperatures, some prefer very high pressures. Okay, so very high temperatures are found in our rocks. Our rock genesis, metamorphic rock genesis, has been involved in high temperature processes, geological processes. So these underlying geological process, interior, okay, Earth's internal geological processes are important. So high temperature geological processes, that means continental collision conditions are found in our region, but not now, some 500 million years ago, okay, at the time of Gondwana. So therefore, high continental collision means, by your first year knowledge, plate tectonics, some introduction you may have learned. there you understand about plate collision. Plate collision means uh, the colliding of continental plates, or whatever the two plates collision is plate collision. But orogenesis or mountain building is happening due to continental collision, right? So this creates a lot of heat due to friction, right? Because of collision, there are a lot of frictional heat is generated in addition to the heat generated by the magmatic processes, right? So this, because of this heat, frictional heat, the material get melted, and that melted material forms magma, and that adds extra heat also, in addition to mantle convection, or the underlying mantle heat flow, right? So therefore, Sri Lanka like countries, Madagascar, southern India, they have suffered this continental collision some time ago, right? Some millions of, hundreds of million years ago. So they, those conditions prefer to form minerals like these rare minerals like corundum, ruby, sapphire, like gem varieties as well, right? So they need specific conditions. So therefore, our countries has this. Our country and others similar countries that we mentioned, like Madagascar, Brazil, they have suffered these high temperature conditions. So therefore, we have similar type of gem varieties, including alumina or corundum family. Okay, sapphire or ruby. In addition, you have a lot of other types of minerals also, right? If you go to Ratnapura, you can find the various types of minerals. So all these minerals were found in rocks some time ago, some millions of years ago, right? Later on, they, after erosion, after weathering of rocks, these minerals are resistant. They are not easily decayed, like feldspar, quartz like thing. They do not convert into soil. Okay, while other minerals are converted into soil, these are retained in the soil itself, because without getting decayed, destroyed, weathered, right? So they roll with transportation of materials with the aid of water, and deposited in low-lying basins. So that is what we call the alluvial type of mineral deposits formation, right? So such deposition might have taken place about some kilometers, some hundreds or tens of or hundreds of kilometers away from the source region. That's why we call them as alluvial deposits, right? So Ratnapuri is one sort of such place where we can see this burial of such minerals. Now we can find them as deposits, right? So that's why you see them as layers, right? Illam, right? It's layers because of this transportation and deposition in layers, right? Sorting and everything is there, because on top of the Illama you have a pebble layer, coarse grain pebble layer, right? That is what you call mala, right? So people from Ratnapur area might know this very well. Okay, so anyway, specific geological conditions are required for genesis of minerals, and the countries like southern Africa, South Africa, what you have is diamond. Okay, diamond is there because they diamond need high pressure conditions. Diamond need high pressure conditions to form. So such countries they have diamond because of high pressure conditions. Okay, so high pressure conditions are required for minerals like diamond. Okay, diamond is carbon variety, right? One form of carbon. So you know what is the carbon? Sorry, what is the carbon form we have in Sri Lanka? We have one form of carbon available as a mineral, industrial mineral. Hmm? What is the mineral we have? Graphite. Yes, graphite is there, but we don't have diamond because our rocks are not subjected to high pressure conditions that require to convert carbon into graphite status, right? But some other countries, they have suffered high pressure conditions due to subduction, right? Due to subduction, not collision. Collision creates high temperature conditions. That's why we have alumina or corundum type minerals, right? But for carbon converting to graphite into what is diamond, it needs more and more pressure, like conditions we expect in rocks like eclogites. Our rocks are granulites mainly. Okay, high temperature rocks. We call them granulites. And eclogites are high pressure rocks. There you can see even diamond. Okay. In addition to that, mantle diamond is also available in some regions, like in southern Africa. They surf on the surface. They found now the diamond which was available in the Earth's mantle, which was carried by special magma type, which is called kimberlite magma. Okay, a special type of magma which dumps a diamond which is coming to the surface, right? So anyway, so like that, some specific geological conditions are required for formation of the minerals. Okay, gem minerals or other minerals also, they need specific pressure temperature regions or conditions, right? So you will learn in detail about these things in petrology courses as well, regarding the stability of minerals. So therefore I'm not going to teach you very much details on the stability fields of minerals, because it's a different aspect you have to learn under petrology courses, right? In the next semester, you will learn in detail about those things. Okay. So as I mentioned, so these specific conditions are required for minerals to be formed, and the uh, the the position of mineralogy related to other earth science disciplines is also important to consider. Okay, there you can see, for example, petrology. Petrology means the study of the scientific study of rocks, right? So for that we need mineralogy. That's why we learn mineralogy before studying petrology. Okay, and geochemistry and structural geology. You all know about these things, right? These terms. And environmental geology, hydrogeology, economic geology. All these geological terms are important because they are subfields of main geology. Okay, but for all of these subfields, it's necessary to have mineralogical knowledge, right? Otherwise, you can't go ahead with even if you try to study advanced studies in postgraduate levels, you will still need mineralogy knowledge. Otherwise, you can't proceed, right? So that's the barrier for engineers, civil engineers, who are lacking the mineralogical knowledge. Okay, so that's how you have to master, and that's why you have to master also the mineralogy in all the types of fields. Right. So definition of a mineral, you already know. Just to revise yourself, it should be a naturally occurring mineral and inorganic substance also, right? Naturally occurring inorganic solid. It should be a solid state material also, right? With a highly ordered atomic arrangement. What does that mean? Highly ordered atomic arrangement means it should be a crystalline material. Crystalline means it has a specific shape, crystal shape. and a definite chemical composition. Definite chemical composition is also there, but you can see within brackets, but not fixed. It says, but not fixed. Definite chemical composition is required, but not fixed chemical composition. You will learn about this thing later on in this course. Why we don't make it? Why we don't need it to be fixed? Because the chemistry can be variable, but it's definite. So what is the meaning of that? Definite composition, but variable. Okay, there are some slight differences there. Okay, so we will learn about this thing later on, how we can address that specific statement. Okay, right. So regarding the history of mineralogy, in late 1800 was a very important time, because the discovery of polarizing microscope was that time. Okay, so discovery of polarizing microscope was happened in late 800. That means 1800 times. So that was the turning point to master on mineralogical aspects, because without the polarizing microscope, people knew only very limited details about the minerals. What you see with the naked eye only, people could understand color and some other features like fractures or cleavages. Okay, and many other properties that you learn under microscope comes after that time. So this is a very important time regarding the properties. So there onwards only the optical mineralogy field started to develop. And then early 1900 time, XRD instrument was devised, and XRD measurements gave people to understand the internal structure of minerals. Okay, the internal structure so far didn't have much knowledge until that time, because regarding the arrangement of this atomic structure, right, structural features, people could not understand until the XRD was discovered, X-ray diffraction. Okay, and then it came development of secondary electron microscope. Right, secondary electron microscope means SEM. Right, secondary electron microscope. It came around 1960s. Okay. At the same time, like 1960s, the electron microprobe was also discovered. So they came almost together, right? Because some electron microprobes are equipped in SEM. Okay, so the some extra components only to be added to the secondary electron microscope. So electron microscope means a microscope that we use to study materials using electrons. Okay, in the optical microscope or polarizing microscope, we used to study materials with the aid of light. Right, instead of light, what we use here is electrons, electron beam. Okay, so electron microscope is also similar to one, that because we use electron beam to understand the chemical composition also. So we can accurately analyze the mineral compositions. So that means we can get mineral chemistry with an electron probe, right? So until that time, people learned about the mineral chemistry only using wet methods, wet chemical methods like titration. Okay, people studied minerals using chemical methods, titration mineral methods. They realized chemistry using wet chemical methods. So from there onwards, we could study minerals or analyze the minerals and get the chemistry using dry chemical methods. That means without dissolution of materials. You don't need solutions. Okay, right. In 1970s, like the transmission electron microscope was discovered. So this is called TEM. Okay, transition electron microscope. So it's another stage of electron microscopy, which also can be used to identify some atomic structures and symmetry. Details about the atoms, atomic structure, atomic scale details can be found in this TEM. Right? In the SEM, we get chemistry mainly, not the structural information. Okay, and in 1980s, the ion microprobe came discovered. Ion microprobe is another device where we use an ion beam instead of an electron beam to study. Ion beam means some ions like cesium, oxygen, or cesium or oxygen. Okay, a beam of ions are used to interact with the material. Then we get some secondary information. In the previous case, we make the material to be interacted with an electron beam and to generate some secondary X-rays. So with that, we get the chemical information. But here, we get again some chemical information, but using ion probe, ion beam, right, instead of electron beam. So we can study about not only just chemical compositions or the elemental composition, but also we can study about isotopic composition of minerals. So that is very important, which helps us age dating also. Okay, it helps us very much about the age dating because we can have isotopic composition determined. So you will learn about these things in detail in your next year in different course modules. Right. So that is a basic background for the mineralogy, and here you will see how our silicate minerals are predominantly found in the Earth's crust. Right? They are dominant. Silicate minerals are dominant in the Earth's crust because the crust is totally made up of silicate materials. You know, Earth's core is made up of metals, right? Iron, nickel, like metals are there, no silicate materials. But the mantle and crust are the places where you can find a lot of silicate materials. And out of that, Earth's crust contains various amounts of silicate materials. You will see the composition in weight percentages. What is weight percentages? By weight. Okay, oxygen 46 46 percent, and silicon is 26 weight percent, aluminum 8%, iron 5, calcium 3, sodium 2, potassium 2, magnesium 2. So these are the main elements that you can find in the Earth's crust. Okay, main elements. So the remaining 2 or less than 2% composes other elements like manganese, chromium, nickel, like other elements, right? You can find only less than 2%, but all the other 98, more than 98% are composed of these elements. So you have to remember that, right? So out of that, you can see here, silicon and oxygen are the dominant elements you can find. So the crust is mostly oxygen and silicon composed, right? If you take the total here, it will come more than 70%. So that means the majority of the components that you find in the Earth's crust is made up of oxygen and silicon, right? Oxygen and silicon are the main components that you can find in the Earth's crust. And then if you take the atomic percentages also, you can see similar variation. So that means it's very, very important that to have oxygen and silicon in the Earth's crust. So therefore, because of this oxygen and silicon dominance in the Earth's crust, you must have silicate minerals dominantly in the Earth's crust, right? It's obviously you must have silicate minerals because of silica and oxygen are the dominant materials that you can find in the Earth's crust. So you can see non-silicate minerals are composing only about 8%, right? All the other minerals are silicates, right? So you have non-silicates only about this much, right? Nearly 8%. So out of those other amount, like 92% remaining portion, you have mainly plagioclase. Okay, you have plagioclase, and then you have alkali feldspar. So that means what the total feldspar population in the Earth's crust is very much, right? It's like more than 50%. Alkali feldspar and plagioclase feldspar, right? So that is very important to know, right? So more than 50% are composed of feldspars, and then comes quartz, which is about 12%, right? Quartz is 12%. You understand? Quartz is 12% only. The main varieties what you have is feldspars, right? Out of that, plagioclase is the dominant. So you know the difference between alkali feldspars and plagioclase feldspars. I think you have already learned, but we will learn in detail in this course few lectures also. Right? And then you have pyroxenes. You have pyroxenes about 11%, both orthopyroxenes and clinopyroxenes. Now you know already about pyroxene minerals. And 5% is like amphiboles, right? 5% amphiboles, and then micas 5%, and clay minerals also account for 5%, and the rest is about 3%, which is also composed of other silicates, right? There are other silicates, for example, tourmaline, silicates, we call them borosilicates, boron composed minerals, right? And also some gem varieties can come into this group, right? So mainly these silicate materials, the dominant silicates are clays, micas, amphiboles, pyroxenes, quartz, feldspars, and feldspars minerals. Okay. So other minerals like other silicates, you have about 3%, right? Other 3%. And in addition to those, you have non-silicates 8%. So what are the non-silicates? There are other groups of minerals, right? They do not fall under silicate group. For example, oxides, right? Corundum, ruby. We just talked about some minerals, gem minerals, right? They are not silicates, right? Corundum is not a silicate; it's an oxide. Okay, it's aluminum oxide, and you can have spinels. That is also an oxide. So other in addition, you have hydroxides, right? Sulfides like minerals, right? There are many other types of minerals which are available in the crust, which are non-silicates. So all these materials we can categorize into different groups depending on their chemistry, right? You will learn about these things later on. So we call them rock forming minerals because the crust is mainly formed of rocks. So therefore these most of these silicate minerals contributes to formation of the crust. So therefore we call them rock forming minerals. Rock forming minerals means they have contributed to form rocks. Okay, understand? Is it clear up to this point? Any questions? Do you have anything to be clarified up to this point? Okay, so please make sure that you have to type your number in the chat box. Okay, just for the purpose of recording attendance, because the automatic record generated at the Learn platform will be deleted by 1 month's time. So therefore, you must type your number in the chat box. Everybody, please type your number, registration number, to make the attendance. Okay, did you hear that? You have to type your number in the chat box. Okay, right. So now we move to some special topic, that is the basic building block of minerals. The basic building block of minerals. That is what we call silicon tetrahedra. Because all these silicate minerals are composed of silicon bearing component. That component we call silicon tetrahedra. Okay, silicon tetrahedra means that silicon bearing component in the minerals. Okay, so depending on the configuration, or depending on how the silicon tetrahedra is connected with other ions or other same structures, same component, that means there can be multiple connections of silicon tetrahedra in minerals, and also they are bonded with some ions, cations. Okay, so depending on that, we can categorize these minerals, different mineral groups of minerals. But anyway, this silicon, you can see here the silicon atom in the center, right? So the silicon atom makes this silicon tetrahedra bonded together. Okay, so you have this tetrahedra, and you have a silicon atom inside, right? So this is connected with 4 oxygen atoms. This is connected with extra 4 oxygen atoms. Okay, so you can see here oxygen atoms are connected. 4 oxygen, such oxygen atoms are connected, and you can see clearly how they are interconnected. So we recognize this bonding as half covalent and half ionic. Okay, 50% covalent, 50% ionic, depending on the electron cloud available around the silicon atom. Okay, so silicon atom, you know, it's 2 plus, its valence is 2 plus, and 4 plus valence is there. Sorry, 4 plus valence is there for silicon, and you have -2 for oxygen. So -2 for oxygen, that means you have 4 oxygen atoms, right? That means -8. -8 will be contributed by oxygen. Silicon is +4. So what happens? You have extra -4 valency available in this structure, right? So therefore, you can see this SiO4 silicon tetrahedra is having a -4 charge. Okay, because extra -1 charge each is available on oxygen, so it is not neutralized. So that means you can understand that this silicon tetrahedra is not neutralized. So it's containing -4 valency, -4 charge there. So that means it has the ability to attract other ions because of that valency. So that is important in considering this building block of silicate minerals. Okay, so silicon tetrahedra is important to understand, to know about these different mineral structures. Okay, so based on this silicon tetrahedra attachment to different other tetrahedras themselves, we can categorize minerals, right? The way this silicon tetrahedra is attached, depending on that way, you can categorize minerals, because you know, since you have one oxygen here, this oxygen can act to bond another set of tetrahedra. Okay, you can have another tetrahedra joined to this in various ways. So this joining procedure is different. So we call this particular oxygen as a bridging oxygen. Okay, so I will show you, because it acts as a bridge in between these two silicon tetrahedra. So we call it a bridging oxygen, which acts as a link between two tetrahedras. Okay, right. So you have some minerals as isolated tetrahedra. Okay, isolated tetrahedra, or that means no interconnection, like in some other minerals. Okay, some are having chain structure, right? That means they are interconnected as a chain one by one, right? These ones are just isolated. And then another set you can find as double chains, single chains or double chains. So double chain means two chains. You have one chain here and another chain here. Okay, so they are interconnected with these bridging oxygens, right? They are interconnected. And another structure you can find as sheets. So you have a sheet-like structure. So this is like a sheet. Okay, so this is a sheet-like structure. That's a two-dimensional sheet. So these are linear structures. These are linear structures, and this is like point structure. Okay, this is a sheet structure. And another group is there that has a very complex type of arrangement, which we term as framework. It's a network, like it's a framework. So for example, you can see quartz here. This is a quartz structure. So you can see the tetrahedra, silicon tetrahedra is here, but it is joined with the other tetrahedra, because there are many tetrahedra here and there. Okay, so they are interconnected in a very complex manner. Unlike chains or sheets, they are interconnected with very complex structure. Therefore, they form framework type silicates. Okay, so quartz is one example, and also feldspar is another example for that sort of arrangement, right? Framework type, network type, or very complex type arrangement. So isolated tetrahedra is displayed by olivine. This is one example, olivine, and single chains are shown by pyroxene minerals. Okay, pyroxenes are single chain silicates. So their structure is made of single chains. Only one chain is there. So you can see here only one chain is there. But double chains, when it comes to double chains, you have one chain here and another chain here. They are interconnected. Okay, they are interconnected. That means they are double chain silicates. So amphibole is one example for that, for double chain silicates. And sheet structure, as I think you are aware, mica contains sheet structure. That's why you can separate mica portions into pages of a book, right? So these are like very thin sheets. You can separate them into very thin sheets. So muscovite, biotite, lepidolite, or this type of micas are some examples for sheet silicates. Okay, so phlogopite even. Okay, these are sheet structures. So framework structures you already know, feldspar and quartz. So depending on the silicate tetrahedra which interconnects with another set of tetrahedra, we can categorize minerals into groups. Okay, and also we since this is a kind of repetition of same structure, right? This is the same structure repeating silica, silica tetrahedra. So it is repeating. So we call it polymorphic. You know, polymorphs. It's a polymorphic type of silicates. Okay. So we will see in detail about these. Sorry, not polymorph. It's a polymerization. Okay, polymerization of tetrahedra. Polymorphs are another thing that we will learn soon in next lecture maybe. Okay. Polymorphs, as you know, polymorphs are the same the minerals which have same chemistry but different structures. Okay, so polymorphs are such minerals. That means, for example, if you have aluminosilicates, you may have heard of aluminosilicates, sillimanite, kyanite, andalusite like minerals, right? They have a similar chemistry, but their structure is different. That means their crystal structure is different. Therefore, they are termed as polymorphs. Okay. So anyway, this is polymerization. That means silicon tetrahedra is polymerized with the aid of and bridging oxygen. Okay. A bridging oxygen is there. A bridging oxygen acts as a bridge in between two or more silicon tetrahedra. So you can see many bridging oxygens are acting in different ways for different minerals, right, to form different structures. Okay, right. So if you briefly consider this polymerization of silicon tetrahedra, here we have different categories, as I mentioned here. The mode of polymerization matters to produce different minerals categories. Okay, so here we have first we have isolated silicon tetrahedra which does not contribute to any bridging, right? So the oxygens are there, but they have two electrons to share. Okay, they have two electrons to share with, but they do not share in first group of silicates. Okay, the first group of silicates is isolated tetrahedra. So isolated tetrahedra we term as nesosilicates. Okay, nesosilicates we term as nesosilicates, which are or what do you get, isolated tetrahedral minerals. Silicon tetrahedra is isolated there. Okay, so we call independent tetrahedron. Silicon tetrahedron is there, right? And the second group where one bridging oxygen is acting to connect to silicon tetrahedra, where we call double tetrahedral unit. So this is a double tetrahedral unit, right? This is a single unit. We call it a double unit, but here it's a single unit. Okay, here it's a single unit. Here you have a double unit, right? So such silicates we call sorosilicates. We call them sorosilicates. And the other one has a way of connection that is we call cyclosilicates. Why we call cyclosilicate? Because they are interconnected in cyclic manner, in a cyclic manner. Okay, so you have cyclic manner interconnection, so which makes a sheet-like structure, right? Actually, this makes a sheet-like structure. Actually, it's not a not a sheet-like, a ring-like structure. Okay, It's a ring, right? Tetrahedral ring. You understand? It's a cyclic structure. So those are called cyclosilicates. And then comes inosilicates. What is inosilicates? Here you will see some silicon tetrahedra are interconnected in a way they form a chain, right? So you can see here they are interconnecting, right? They are connected like a chain. You know, chain, they are interconnected through a bridging oxygen. They are interconnected through a bridging oxygen. And you can see this can have infinite number of tetrahedrons, right? It depends. So since we have a single chain here, we call it single chain silicates, right? Single chain silicates. So it's a chain structure, inosilicate. We call it inosilicates. And there is another type of inosilicates. As I mentioned in the previous slide, two chains are interconnected, right? So here you have one one single chain, and there is another chain silicate here. Okay, so these two chains are now interconnected with another bridging oxygen here. Okay, so it's like repetition of these units is happening. So that's why we call it polymerization. So this polymerization can take place in different ways, in different forms. Sometimes they make some like ring-like structure. Sometimes they make a single chain structure. Sometimes they make a double chain structure. So here, infinite double chains can be found in this structure. So this is another type of an inosilicate where you have two chains instead of a single chain. So two chains means they are interconnected again. And another type we have, it's like sheets, tetrahedral type. These silicon tetrahedra are joined like sheets, right? So you have, it's in the previous case, cyclosilicate, you have just a single ring only. But here, not just a single ring. Here you can see it, okay? It is interconnected with another ring there, okay? But it's not in a way of like a chain. It's not like a chain, right? Because this is more wide, right? This ring-like structure is more wide, so that makes everything like a sheet. Okay, so therefore we consider them as separate sheets. Okay, so that's why we call them as a sheet structure, or in other words, the mineral category we term as phyllosilicates. Okay, phyllosilicates. So this is a sheet like structure, a little bit complicatedly interconnected. So they form they form a sheet like structure. So for example, mica, that is the way they are formed. That's the way they are formed. Okay, right. And the other one, the tectosilicate, which is very difficult to graphically show in a diagram like here, two-dimensional diagram like here, right? There are infinite number of networks. In the previous cases, we have very different structure than this one. Okay, so it has a network type of structure, but I think you can easily understand if you see this image here, this figure. Okay, it's a network type configuration. So if you see the plan view from the top, right? Plan view, you know, the plan view, it will look like this one, this diagram. Okay, so this is how it is interconnected, and you see the bridging oxygens here and there, and they can interconnect many more silicon tetrahedra, so that they will form a very solid network of tetrahedrons. That is what you call tectosilicates. Okay, so this is the a special type of silicates. Now you understand that all this polymerization is caused by oxygens. This specific oxygen which joins with another atom. Okay, so if anything is not joined in the structure, that is not a bridging oxygen. Okay, so if another tetrahedron is joined in through a oxygen atom only, you call it a bridging oxygen. Okay, so all the adjacent silicon tetrahedra can share corners. Okay, uh, if an oxygen is there, right, the shared corners are called bridging oxygens, right? These shared corners are called bridging oxygens because they interconnect through an oxygen. Because in the center, what you have in a silicon tetrahedra, in the center you have a silicon ion, right? Silicon ion, so it has 4 plus valency there. So if you make two silicon ions close together, if you make two tetrahedrons close together, right, what would happen? So if you want to close them together, each other, right, you have +4 here in the center and you have another +4 here in the center. So what happens? They have a high repulsive force, so they do not easily come into close to each other. Okay, so they have a high repulsive force, therefore it's very difficult for them to be connected. But because of an oxygen is there, only they can interconnect with that oxygen, so that they will be staying away as much as possible without being attracted, right? They are joined together, but as much as possible they get rid of being close to each other. Okay, so you can understand how they are repulsive because of this +4, 2 + 4, that means they are highly repulsive. So therefore that's why you see some space in between, some distance in between these structures. Okay, they are not easily made themselves close to each other. Okay, right. So do you understand this part? Do you understand about this categorization of silicates based on the polymerization effect? Is it clear? Tell me. I need feedback. Did you understand about these categories? Yes or no? Yes or no? Okay, yeah, I can see people have responded in the chat. So you have to be you have to study thoroughly about this polymerization of silicon tetrahedra, right? So you search in the internet also, because now you don't have access to libraries, so therefore you can find it in the Google, how you can learn about silicon tetrahedra and their polymerization uh, as additional reading materials. Okay. Right. So please make sure everyone type your number in the chat box to make the attendance marked. Right. Okay. So we will take the first group. We'll take the first group. We'll take the first group. We'll take the first group to study. Okay. Nesosilicates. That is nesosilicates. So we will go with that first. or in other words, we call it independent tetrahedra. Okay, so what is independent tetrahedra? So you can see the tetrahedra, they are independent, right? So these they are not connected, like they are not polymerized. They are not polymerized like uh, in the other examples in units, right? So they are, for example, here you have a tetrahedral unit to form a chain or something like that, right? So these are not like that. This is just a single unit there. Okay, so the basic structure or the basic chemical formula or the unit composition can be termed as this. Okay, X2SiO4, X2SiO4, right? That is the unit composition of nesosilicate. So often X is 2 valence. That means it's a metal, right? 2 plus metal. For example, magnesium, ferrous, like metal. It's a valency that you can find. And since they are isolated, okay, since they are isolated, they have, I mean, they don't want to share bonds. So if they want to share bonds only, they have to use a shared oxygen or bridging oxygen and then form a bonding in between. But these are non-bonded structures. They are just packed only. They are just packed, tightly packed silicon tetrahedra. Okay, they're just packed only. So they, because of this packing, heavily packed structure, they have a higher density, right? High hardness also, and such features are very common for this densely packed silicates. Okay, because of that repeating structures there, I mean, like in the chain silicate or in ring silicates or something like that, they are lacking such kind of a polymerized structure. Therefore they do not have good cleavages. They don't have good cleavages. So they don't have good cleavage means, what do you understand by that? Can you easily break it, or it's easily breakable? If you have a cleavage and if you don't have a cleavage, how can you recognize in terms of breaking the material? Cleavage means the breaking planes, right? If you don't have breaking planes, that means if you don't have cleavages, that clearly indicates that it's very difficult for you to break it, right? So it's not easily breaking. So that's what you should understand by poor cleavage, right? So these minerals are not easily broken, right? For example, if you drop from some height to minerals which are having a set of cleavages, and those are not having cleavages. If you drop them onto a rock or onto your cement from a height, you will easily get broken the mineral that has cleavages, right? You will see it will break into pieces along those cleavages easily. But the one that did not have cleavages will not break easily. It might produce some fractures, but it's not easy to break, right? So that is a feature of tightly packing structure. And there is a low degree of substitution because most of the silicates are having aluminum as a substitution. Okay, but in these minerals, in these nesosilicates, you have less amount of substitution. Okay, less amount of substitution with silicons. So therefore, mainly you have iron or magnesium as the substituting phase, or substituting iron, cation in these nesosilicates. Okay, so iron and magnesium can be there. So this general formula X2SiO4, general formula can be like this. Okay, iron, magnesium, both can be there. Even one can be there, but both also can be there, right? As a silicate. So those are nesosilicates. Or in other words, independent tetrahedra, right? Independent tetrahedra. If you consider some common cases, right? As I mentioned, this is olivine, that is the composition. It's a common tetrahedra or nesosilicate, common nesosilicate type of a mineral. Okay. So olivine is greenish color, right? Olivine is a greenish color mineral which is available abundantly in the Earth's mantle. Okay, not in the crust. Crust also you can find some to some extent, but mainly olivine is found in Earth's mantle. One reason is we learned that low degree of aluminum substitution. Okay, low degree of aluminum substitution in these minerals. So olivine does not have aluminum. So olivine does not have aluminum because it does not prefer aluminum. But in the crust, aluminum is has in high quantities. In the crust, you have aluminum in higher quantities, right? So we learned about the composition of the crust, right? So there you can see aluminum is the next to silicon, right? So aluminum is next to silicon, but since aluminum is not preferred in olivine structure, there is no way for olivine to be formed in the crust easily. So, but it is possible because you have enough abundant iron and magnesium in the Earth's mantle compared to the Earth's crust. So therefore, they prefer to be formed in Earth's mantle. So olivine is a common mineral you can find in mafic and ultramafic rocks. So that's why we call mafic and ultramafic rocks, which are dominant rock types found in Earth's mantle. Okay, for example, gabbros or peridotites. Ultramafic means peridotites. So you will learn about these rocks later on in under the petrology. But just for the time being, you can remember that mafic and ultramafic rocks are abundant in the Earth's mantle, not in the Earth's crust. Okay, so anyway, they need high temperature conditions to form. So therefore, in the Earth's mantle, you have always high temperature conditions, and it commonly alters to serpentine when it get exposed to the atmosphere. They get altered into serpentine. So you know, serpentinite deposit we have. Where do we have a serpentinite deposit? The rock which is mainly composed of serpentine. The mineral serpentine is called serpentinite. Okay, a rock which is mainly composed of a mineral called serpentine is called a serpentinite. Okay, where do we have a serpentinites in Sri Lanka? Yes, tell me, anybody? Where do you have serpentinite? Does anyone know? Have you heard of Ussangoda? Have you heard of Ussangoda? Yeah, it's not exactly gold. It's down south, close to Hambantota. Okay, Ussangoda region. When you go to Matara, in that region you can find this Ussangoda, and also from Ambilipitiya, southeast from Ambilipitiya, and there are some other locations in the near Ambilipitiya also. What you have similar serpentinite deposits in Indicola Palace, Ginigal Palace, Udawalawe, right, in that region. Okay, we have such serpentinite deposit. That means altered olivine, right? Those are altered olivine, not the pure primary mineral. Those are secondary minerals. Okay, anyway, they have a very nice olive green because of magnesium, and it can be black also. Olivine can be black due to high iron content. If it is magnesium rich, it's olive green, right? So even very black olivine can be uh, found also. And the optical properties, I think you already know some of these optical properties. You may have not chance to study about olivines yet, I think. Okay, but we will see how we can find them in the lab when we have practicals. And there is possibility for solid solution. So we will learn about solid solution later on separately, but for the time being, solid solution means it's a compositional variation of two or more elements under solid state conditions, right? Solution, you know, it should be a liquid, right? In a solution, you know, different types of materials can be dissolved, right? So you can dissolve materials in a solution, but in this case we have materials of varying composition mixed together in a solid phase. So it's like a solution, but this solution is under solid state, so therefore we call it solid solution. So you saw the olivine composition here. I mentioned iron or magnesium can be there, right? So this iron or magnesium can be there to form olivine, right? In variable proportions. There can be variable proportions. So there, because of those variable proportions, you get either greenish appearance or blackish appearance in olivine. So if it is highly enriched in iron, then the olivine is more blackish. Otherwise, it will be more greenish. So that indicates iron and magnesium can be there in variable amounts. So this variation is highly temperature sensitive. Okay, based on the temperature conditions, you can find these variations in these minerals. So therefore, solid solutions are highly sensitive to temperature variations. So we consider these mixing type of behavior as a solid solution in mineral. Okay, so now you might have a question. I mentioned that by definition a mineral should be having a definite chemical composition. Okay, so we mentioned that definite chemical composition, but now I am telling that this iron and magnesium can be variable. This iron and magnesium can be variable. Now I am saying so. So what is the meaning of that? Okay, what is the meaning of this variation? This meaning of this variation. So if you consider the definition, if you consider this definition again, right? So I mentioned that definite chemical composition. I mentioned about definite chemical composition. So now I am telling that it's not it's not it's not definite. Now I am telling it's not definite or something. I am now telling iron and magnesium can be variable in olivine. So in that case, how can olivine be a mineral? No. Variation means it's not fixed, right? I said olivine can have iron and magnesium. Iron and magnesium you can have, right? So this iron and magnesium can be variable. I said it's temperature sensitive, solid solution. So this iron and magnesium can be variable. So it doesn't mean that it is there in 1-to-1 proportion or something like that. Because depending on the temperature pressure conditions, this proportion can be variable. Okay. So that means the chemistry is not fixed. That satisfies our definition. But what is then definite chemical composition if it is not fixed? No, it's definite. Yes. Why? It's variable iron and magnesium, not calcium, magnesium, manganese, or any other thing. It can't come up. I mean, some other element cannot come into this, right? It's definite that olivine has iron or magnesium, right? Definitely olivine has iron or magnesium, not calcium or nothing, other elements like aluminum or something like that, right? So that means it has a definite chemical composition, but it's not fixed, right? That means amount of iron and magnesium is not fixed, because you can't fix it, because it is changeable due to pressure and temperature conditions. So therefore, remember the definition of a mineral there, the iron and magnesium composition can be variable. That's why we call it not fixed, right? But it is iron and magnesium, right? Nothing other than that, right? Therefore, we can have a definite chemical composition also, right? So olivine has a definite chemical composition, but its iron and magnesium ratio can be variable, right? So that iron and magnesium cation chemistry can be changed, but silicate or the silicon tetrahydride is bonded with magnesium and iron, so that is definite. So therefore, this is how our this material becomes a mineral without being deviated from its definition. Okay, so this is how we can identify one of the nesosilicate mineral, which is olivine, right? Okay, any question? So do you have any question up to now? Right, so we can consider some optical properties of olivines once we have practical classes, but actually we don't have, sorry, we don't have uh, much opportunity to get the practical exposure, and soon if we have any chance you will learn about these things in detail, because it's very important that you learn in detail about these things. So if you see this olivine in a thin section, in a petrographic thin section, right? You know about thin sections so far under optical mineralogy, but I understand that you don't have the opportunity to do practicals or getting the hands-on knowledge about these ones. But if the condition of the country permits, you will have chance to make a rock thin section also. Some rock thin sections you have to make by yourself, right? It's a training, so we have to do that as early as possible, because otherwise some theoretical aspects you might not understand. Okay, right. So this is how you see olivine in the optical microscope. This is the cross polarized V, CPL. You know cross polarized V. I think under optical mineralogy you have learned already. When the both polarizers in the optical microscope or the polarizing microscope, the lower polarizer and upper polarizer or the analyzer, right? When you cross it, you will get the colors, interference colors. We call it interference colors. And these are the interference colors of olivine. So this is the olivine grain, very typical color. Is this, right? You can see higher order colors, slightly higher order colors, not very high order colors. You will see in olivine. So this is also olivine, right? This is also olivine, and this is also olivine, and these are also olivine, tiny grains. Oh, sorry. Yeah, cross polarized light, not CPX, CPL. You might confuse with clinopyrrhus. This is not clinopyrrhus. This is olivine under CPL. Okay, cross polarized light. So you have big olivine grain here, and you have tiny olivine grains also. right? Actually, the pyroxene also look like this, right? Clinopyroxene look like this grain, but this is not clinopyroxene. This is an olivine grain. So depending on the thickness of the thin section, also there is possibility for changing of the colors. So this does not show real olive green color. Actually, olive green color is shown in the hand specimen, not in the thin section. Okay, but in the in the thin section also you will see some characteristic color, but you can't clearly see that in this image. But later in the next lectures, I will show you some characteristic colors, and also the demonstrators will show you some practical aspects, and they will schedule classes with you. So make sure that everybody can attend to those classes, because since you don't have practical exposure, they are going to show you some practical demonstrations. Okay, they will show you some videos and some practical demonstrations. So definitely you should attend those classes, otherwise you will be in trouble in the examinations. Okay, you will have difficulties in examinations, and therefore you must attend the practical demonstrations, online demonstrations, which will be scheduled from next week. Right. So we learned about the first nesosilicate type, that is independent tetrahedra, which is olivine. uh, so far, there are several nesosilicates. Actually, there are many nesosilicates, but we are not considering all of those. We will choose some some important nesosilicates and get their important features in the next classes. Okay, so I'm going to stop here for today. So if you have any questions, you can just post now. So do you have any questions?